Welcome to this web lecture on electromagnetic waves and antennas, which is part of the master course Microwave Engineering. In a previous web lecture I talked about the history of electromagnetic waves, and in this web lecture I want to briefly talk about the history of antennas. And I'll be doing that by discussing the experiments by Heinrich Hertz, the way Heinrich Hertz showed how radiation emanates from a dipole antenna. Then I'll briefly discuss the early work of Guglielmo Marconi, and I'll talk about what Marconi called finding the right antenna. So let's start with the experiments by Hertz. This is the man. What he wanted was to prove experimentally the Maxwell equations, and most of all prove the existence of radio waves, which are electromagnetic waves radiating at a frequency much lower than that of light. For that, he made this experimental setup, which we recognize now as maybe the world's first radio system. It consisted of an electromechanical resonator, which consisted of a high voltage transformer with a mechanical interrupter. High voltages were fed into a spark bridge, and this spark bridge was connected to two metal rods, which we recognize nowadays as a half-wave dipole antenna. Connected to this dipole antenna were metal spheres that could be used to tune the transmit antenna. On the receiving antenna, which was placed at several meters distance, he could observe sparks. The receiving antenna consisted of a single loop ending in a spark bridge. This is a photograph that Hertz himself made of his experimental setup, and we're talking about the year 1886, 13 years after Maxwell first wrote down his Maxwell equations. Heinrich Hertz also showed in beautiful graphs how radiation originates from a dipole antenna, which we will show in a very simplified, brief way. Before we do that, we have to remember that the origin of radiation is the acceleration or deceleration or charge, or in a practical system, a changing current in a wire. Radiation will occur in all directions with the exception of the direction of the current itself. We are going to apply this to a short dipole antenna. We have an oscillating voltage source connected to two short metal rods, which are perfect conducting, and we will look at different instances of time over a period. We will start at the time shortly after we switched on the generator. And what we will see is that charge will start to build up in the two parts of the dipole. We draw electric field lines going from plus to minus as indicated. These electric field lines are perpendicular to the conductors because those conductors are assumed to be perfect conducting. And we indicate the current flow by the white block arrows. From this time we move to a quarter of a period. What we see is that the current is at maximum. The most amount of charge has been distributed over the two parts of the dipole. The electric field lines are as indicated, and they have extended in space over a distance of a quarter wavelength. And now we look at the time shortly after this period, so that's t/4 plus. The current has become smaller, which means that charges are now traveling in the opposite direction, and the way we want to indicate this is by drawing electric field lines in the opposite direction, like the one shown here in a dashed line at the origin of the dipole. Next we look at the time just before half a period. The charge has nearly gone to zero. The current is also nearly zero. The electric field lines concentrate on the tips of the conductor. The opposite directed field lines should also originate from the two tips, but for clarity I've drawn them in this way. The electric field lines have extended to a distance of half a wavelength. If we are at exactly t/2, half the period, all the charge will have gone and the current will be zero. And if we look at the period, at the time closely after this, what we'll see is that the two conductors are neutral, so electric field lines don't have to be perpendicular to this conductor anymore, but electric field lines have to be continuous, and the only way we can make them continuous is by connecting them to the oppositely directed field lines. And what we get is these electric field loops that have detached themselves from the antenna. So this is how radiation occurs. And we have to bear in mind, of course, that we also have magnetic field lines which are perpendicular to the electric field lines. Of course, these field lines are everywhere around the antenna, and if we look at a planar cut at half a period, we get this picture, and if we look at the whole period, we get this picture. So Heinrich Hertz fully understood what was happening. What he didn't see was commercial potential. He once claimed that these radio waves he discovered would not have any practical purpose. That sounds funny, but we also have to bear in mind that he died at the age of 37, so he didn't have the time to evolve an idea about practical use. Luckily, Guglielmo Marconi, this is the man, did see the potential of using radio waves to transmit information. He started conducting his experiments at his father's estate close to Bologna, and to be specific, he started in this room. This building is still part of the University of Bologna, housing the electromagnetics department, and inside the building they still have all the equipment of Marconi. And what is for me the most interesting part is this, which is the first transmitter Marconi used in 1894. With this transmitter, he was capable of transforming information in the form of Morse code over the length of the attic of his father's house. Then Marconi moved outside and he could transmit messages soon over distances in extents of 1 kilometer. And later, during a speech he gave at the reception of his Nobel Prize in 1909, he showed this picture and he explained that his success started by finding the correct antenna. What he used later was what was called in those days an elevated wire. So here we have the transmit antenna. This is the elevated wire. And what he soon found was that instead of using a whole dipole antenna, he could use half a dipole antenna, which we call a monopole, have a ground connection of a spark transmitter, and the image in the ground would form the other part of the dipole antenna. He was successful, as we know now, not only by finding the right antenna, but first of all going to lower frequencies, where he could generate more power. And then he found that if antennas were resonant, the length equal to half a wavelength, he would get the best result. He used the same setup for his receive antenna. Was it all due to Marconi? Well, not entirely. He went to the United Kingdom, started experimenting there, founded the Marconi company, and one of the smart things he did was hiring this man, Professor Ambrose Fleming. And it was Ambrose Fleming who understood the physical principle of the monopole antenna, and he was the first who gave a mathematical description. In his 1906 book, you can find this. Was Marconi the father of radio? Then this forgotten man, Fleming, can be seen as the father of antenna theory. With what we have done now, describing the history of electromagnetic waves and describing the history of antennas, I think we have the material necessary to go to the regular part of this course and dive into the mathematics and physics of antennas. If we understand how antennas work, we can come up with new designs which might be necessary in the modern world. So, to summarize, we have seen that Hertz, by experimentally verifying the theoretical work of Maxwell, made the first radio. He understood completely how a dipole antenna worked. Marconi was the first to see the commercial potential, and he found that his success depended on finding the right antenna. So this is the starting point of antenna theory, and more subjects related to this will be shown in new web lectures, which I hope you will attend. So I thank you very much for your attention and hope to see you in the next web lecture.